Welcome to another exciting episode of the Value Engineering Experts. Today, I've got an interesting guest and an interesting company that sells basaltic rebar. Basaltic or glass bar, I believe it's from Europe, is a good value proposition because it's completely inert in its corrosive tendencies, and it's quite cost effective. It comes in a variety of sizes. The company is MEDA Design and Engineering and Technical Services. And I've got two individuals, David Lawn, PEng, who I know quite well, and an engineer of his, Jamshed Zora. Their 188 number is 188-518-6332. So today we hope to talk with Robert Higgins, assisting. Robert, as many of you know, has helped me on two recent podcasts on E5, the miracle admixture, going through the revolution of potentially proving 1,000-year mixed design. It's nano-colloidal silica, invented by Joe Shetterly, a finisher. So we're going to talk about how those two products might blend together. And I look forward to having a good session with David Lawn. He's quite articulate, does a number of things in Windsor, Ontario, which is close to Detroit. And I believe he has a US sister company that does the basaltic bars. In any case, welcome to the Value Engineering Experts. I hope you enjoy the show today. Thank you. Welcome, David, to the Value Engineering Experts. Really appreciate it. I'm happy to help you guys. Your company is called Texon GRP in terms of the bar product. Is that branded in the US as well?
Yes, it's Texon Grizzly Reinforcement Products. So we went with Texon GRP, which is Texas and Ontario, because of our relationship with Texas and Ontario. And then the grizzly is sort of speaks for itself in the logo, and the tree is of course, Ontario's provincial tree, and then the star is the Texas star.
Robert, we did a patent that involves FE Spiral. It's called. It's a 75-year culvert patent, and David was very helpful. But we were able to get. He's got 4-millimeter rope. So he's able to generate, I think it's 100 feet long.
We can do thousands of feet if we need it.
Oh, so it was very useful. Like one of the patent itself that went with the culvert, which was a plastic plank HDPE. It was like a double Dutch skipping rope. So it's quite innovative. Then that was one of my better thoughts for that, because it was hard to do the 2 inches of reinforcing between the old culvert and the new with the plank. Yeah. Anyway, I think you understand that stuff.
Yes.
So Robert, I thought was a great guest to have today, David, because Robert Higgins has got 45 years experience, is very well regarded in the States, has a lot of integrity, and has worked for meaningful corporations and been a consultant for a number of years. Jamshed and David have a successful business, and I think you're doing a broad range of engineering, right, David?
Correct.
Somehow you got into this bar. And I think we share this sustainability interest, even with Robert. Robert and I are quite excited about E5. So E5 is nano-colloidal silica. And to be clear, it's just growing into a presence, specificationproducts.com in the States. Robert's hired as a consultant and retained by them. So Robert has really done his homework on that product. Totally unique in the sense that it holds the water. It almost makes the water heavy. You get rid of all wet cure labor. You don't have the plastic shrinkage cracking, which has a tremendous opportunity for, in my opinion, your fibers. Like they're using E5 admixture in ICF systems, in insulated concrete form systems, without rebar. And, my belief for sustainability is that we use too much rebar. And if we can get rid of the cracking, which is nano-colloidal silica does, and get dimensional stability, all of a sudden you've got things like Infinity Slab, which uses helix fibers and they're going to 100-foot saw cuts. 100-foot saw cuts.
Wow.
Wow. Did you not know that, Robert? Yeah, 100-foot saw cuts. They call it infinity slab, but that's a partnership with Joe Shetterly. Again, Purdue University was key with that. So now we can talk a little bit about MEDA's products, where we're really trying to get Robert familiar with that. And I think it's a very marriage, because I love the non-steel. You know, I like that stiffer yield curve. So it's a brittle fracture on a bar. Like you're not going to get the running time, what we call it as civil engineers. But you don't need it when you're properly within the yield curve. So everything's going to be crack resistant in these applications when you model them. And I'll let David do more of the talking, I think. So David, your support, Jamshed, we're going to be able to call you as well, I hope, or people can.
Of course they can.
Get your cell phone number. Well, I'm bad that way, Jamshed. I'll give the cell phone number out on the But, you know, it's about service. And you know, I always found, Jamshed, you know, just a tip for a young guy, you know, if you return the calls in 24 to 48 hours, you get a reputation, and that'll help David, because they won't bug him. Oh, I didn't hear back from Jamshed, right? Anyway, I'm sure you're having a good experience with David. He's a good guy. David and I were introduced by a bank, you know, by a friend at the HSBC bank, Robert. But why don't you guys talk a little bit, and I'll get to know Robert now and some of his background. Robert, quickly give us the 10,000-foot view of what you've done over the years.
Okay, well, I got involved with waterproofing concrete back in 1976, and started my own manufacturing company in 1979. And while I was manufacturing, I did a lot of analysis. I geek out pretty easily, where I find things really interesting if there's a technical issue, and I love really tough problems. I got presented by one because I wrote an article for Construction Specifier Magazine, which is an international magazine for specification writers. And an attorney contacted me and got a hold of me and asked me if I would get involved with this lawsuit. And it was a major case. It was with the Hotel del Coronado in San Diego, world famous hotel, and the owner's a gazillionaire, and everybody's excited. And the engineer was pretty stressed out because his feet were being held to the fire about certain things that were done to the building. And the reason why they called me is because I did this article on carbonation, which, you know, we'll return to that some other time. But, you know, why they want to carbonate concrete is beyond me, because you actually don't want to do that, but that's another issue. But anyway, I said, well, let me do a document review and I'll tell you if I can take the case. So I reviewed the documents for a week and I got back with an attorney. He said, do you think we can minimize our exposure? I said, why minimize it? We can win this one. He said, we can't win this one. I mean, here's this expert. Yeah, all these experts from all over the world were in there, and the most highly regarded. I said, well, they missed a really important point. I said, what's that? I said, well, they're citing an ASTM, an ACI standard. I said, yeah. I said, well, that didn't exist when the building was designed. And I said, and the chloride content of the concrete, what they're showing in the samples, is too uniform. That is not caused by seacoast structure exposure, as they're trying to state. I said, well, wouldn't it even out to like that? I said, no, it would go back and forth, and yet you'd have concentration areas, and that's not doing that. That's not what concrete does. So then when I had them analyze it for the type of chloride it was, turned out it was a ready mix manufacturer that put calcium chloride in because they were doing these precast units during the winter. So it completely absolved the engineer, and that made me kind of famous overnight. So I've been doing construction defect litigation ever since then. And I've gone out, and one of the most fun projects I ever did was the London Underground. I was flown out there in the middle of the 1990s and went out there a couple of times, ended up waterproofing 60 miles of the tunnel, something they didn't think could be done from the inside without major renovations and major repairs. We were able to do it for not even 10 cents on the dollar for what they were forecasting. And then had even a bigger challenge when we had this Hawaiian tunnel. It was called the H3. It was the biggest civil project of its time in Hawaii. And they literally put this tunnel through the bottom of this mountain. It was leaking like a sieve. And so anyway, I'm talking to general contractor, and they're freaking out because they can't open because it would damage the cars with the alkaline moisture. I said, well, we can fix that. He said, well, you can't fix this. I said, so I looked at him and said, hold my beer. I said, we'll do some test areas. We did 2 test areas, they dried out. Can you do a couple more? Did 2 more test areas, they dried out. We ended up drying out the tunnel in a period of 2 weeks, and it's stayed dry ever since. So those are the kind of projects I get involved with, where concrete experts say, well, you can't do that. I found a lot of people in the concrete industry don't really understand concrete. They're reciting information they've been told and led to believe by others they believe to understand the problem that don't either. This is all inherited bad information. So I love to get involved with things like what you're doing, where I can get rid of the bad information and get involved with things that work. That's probably the best way I can explain it. And I'm a chemist, so I've developed different products to treat concrete, and I still enjoy doing that, but not as much as I like solving problems.
And now with E5, you were going to actually do a colloidal silica, were you not?
Yeah, years ago, I was going to introduce that to my old company, but I decided not to because the company was heading in a direction I didn't want to go. So I ended up resigning from the company I founded in 2009. And I was approached by several companies to work, but I didn't want to be an employee. I like being an independent consultant. And one of the really fun assignments was a long one, went for almost 5 years, was with XL Brands Adhesive. They're now a division of Bostik. I helped them redo most of their literature as far as and warranty language and technical tightening of their technical data, because sometimes they would refer to, say, pH and alkalinity as interchangeable terms. I said, do not do that. Those are totally different. Those are separate and apart. Don't confuse those two. So I gave an example how you can increase alkalinity and lower the pH. I said, if you take an egg and you put it in water, it has a very low alkalinity because the calcium carbonate in it is very low in solubility. You add a little bit of, and you say you start out with tap water that's just 7.5 pH. Well, if you add vinegar, the pH of the water will drop temporarily, but as it starts dissolving the calcium carbonate, the pH will rise a little bit, but it stays down in the neutral area. Well, as you keep adding vinegar, it keeps dissolving the calcium carbonate. So that's increased the alkalinity, but it doesn't necessarily increase the pH. So people do not understand there's a clear delineation between pH and alkalinity, and a lot of them are nonlinear in their concentration, and that's especially true with concrete. So those that don't deal with the chemistry in a proper way often find themselves tripping over themselves, running into problems they couldn't anticipate because they weren't taught the information correctly. So that's what I bring to the table.
That's quite useful, I think, in expert witness work. But listen, David, why don't you give us your challenges and your successes in terms of, you seem to have a bar that's well priced compared to, let's say, FRP, correct?
Sure, Martin. Thank you. And I have to tell you, Bob, that's quite impressive. I really appreciate hearing about your background. And Jamshed and I and all the other engineers within our organization, we constantly tell them, don't believe all the things that you read, and don't believe what people tell you about concrete, because most of them don't know the real nuts and bolts on concrete, and they don't understand it, and especially things like alkalinity. And certainly we've even discussed some of the challenges as it relates to alkalinity. And Martin, the nice thing about mentioning about the rebar, and of course the other products that we'll mention a little later, is that it isn't susceptible to a lot of the issues we have relating to alkalinity, except in its fiber form. And in its fiber form, it can be, but with the E5 that you fellows have talked about, we can mitigate that concern, where we have the issue with respect to alumina salts and alumina interacting with the concrete, with the alkalinity, thereby causing the hydrogen gas, which is a concern. We think, based on the conversation we had earlier, we should be able to address that. So that in itself, that is a huge bonus, because the fiber, as we talked about, when you put rebar or a mesh into concrete, it's not a homogeneous mixture. Whereas when you use fiber, depending on how you introduce the fiber can be your friend or it can be your enemy. And a lot of people think that, oh, well, my slump looks a little bit large, too big. I'll add a little water at the truck. But what they're doing is they're automatically now diluting that concrete and taking strength away. So the best way to add any fiber is to try and dry mix it if you can. That's the first thing. The second thing is, of course, that when you're using any of our products, generally the alkalinity, and we've talked about differing concrete availability today in terms of standard ready mix or even bagged concrete, for example. Higher alkalinities and other issues that are a real issue. For example, with the rebar is actually coated, as most FRPs are, with an epoxy, because that's how we hold together the fibers or the roving of the strands. But it's only there temporarily until the concrete sets. Once that curing process is done, the epoxy really doesn't matter anymore. It does, but it doesn't, right? So, and the beauty of our FRP is that it has a very low creep rate. Basaltic bar has basically the expansion coefficient the same as concrete, so it doesn't work against the concrete. It's resistant to alkalis, as we've noted. It is roughly around 2.5 times the tensile strength of steel. It's a quarter the density. It won't conduct electricity. It has some really great features that other FRPs do have and don't have. So, for example, glass has boron, which is a nasty thing. And the creep is a little bit different as well. Also, it's made from glass. When you look at, Martin, you and I have talked at nauseum about this because we both have a passion for it, and that is looking at things that are good for the environment. And this particular material, all of the hard work was done by Mother Nature, because Mother Nature did all the smelting, if you will. So when the basalt rock is mined, the only thing we need is a high heat source, which you can create with a low heat source. You have to have a transformer to do that. And it's cost one way or the other. But you can basically melt this in a furnace, and you can create this roving, which is then the fiber, and you have a very, very low carbon footprint. The beautiful thing about the material, though, is that not only does it have a low carbon footprint, not only is it naturally occurring, but the benefit is it's like a circle economy product, because when you do find an end of life situation, it can basically be ground up just like you do your concrete, and it won't have any adverse effect on the reuse. Because of that, it's perfect for earth touching applications, high moisture applications. You won't have the same issues we do with contamination with a lot of the other reinforcing agents. And the other thing is because it has the same coefficient of expansion as concrete, roughly, very, very minor difference, it can literally be laid right at the surface. So you don't need a corrosion cap anymore. So think about the savings, the carbon footprint savings just on that amount of concrete. If you have to have a 3-inch cap, you don't need it anymore. Knowing that the material has, those inherent benefits, and looking at the potential for it, it's a real challenge. And as Bob said, right, everybody thinks they know about concrete, and they think you tell them, what, your pH is not right, but it's okay because they think their alkalinity is in line, right? They're like, they don't get the correlation between all of the chemistry to make a perfect concrete structure. So with now the advent of a lot of these lightweights where they're using post-consumer materials, we have found by introducing either our fiber, because there's a low alkalinity, so it doesn't have any adverse effect per se. I still like this idea of E5, and I think it's a good thing to have as a countermeasure, just to be on the safe side, because it doesn't cost that much, but it costs a lot to pull up a slab. So, right? But in looking at that, we've seen with some of the lightweights, because they internally cure, Martin, we've even beat the 100. What did you say? The 100-foot? What did you call it? The continuous?
100 by 100, yeah. 100.
Yeah, okay. We've actually
infinity slab.
Yeah, infinity slab. We have not saw cut some of the slabs we have done. So we did a slab not so long ago. It was actually on television. It was a 6-inch thick slab. I believe it was 60 by 120. And the fellow who was in charge of the job forgot to order the saw cutters. So he says to me, and he's got a bunch of sensors in there, and I'm looking at the numbers, and because of course it's a low temperature cure, I'm looking at it and it's like between 90 and 100 degrees. So, between 35 and 36 C. I said, don't bother. He goes, what do you mean don't bother? I said, you're not going to need it. He goes, why? I said, this is not going to crack. And I said, and if it cracks in 2 days, it's not on us. It's your base. He said, no. He was down there for a week and a half with a flashlight looking for micro cracking. He could not find anything in that slab. So I would challenge you to take a look at the opportunity to try and use the fiber, and we would tell you the proper dosage. We actually have a number of published papers and peer journals that we have undertaken over the years to make sure that what we are saying is in fact true. Some time ago, when I first started getting into the basalt, the gentleman who introduced it to me was Dr. Madagula, and at the time he was the associate professor at the University of Windsor. And I thought he was out of his mind when he told me about this product and what it could do. And I said, no, I don't believe you. And he was telling me about it. And so we started looking at papers, and there were a tremendous number of papers available, but all of them were very odd in the sense they had specific information and the data didn't make sense to us. So I said, you know what? We're not even going to pay attention to these papers. Let's do our own. Let's take our product and let's do the research on it. So for the last 13 years, we have been working closely with the University of Windsor, which, by the way, has, I believe, the largest structures lab in Canada now. If not, it'll be the second largest, but I believe it is the largest. We have been working with Dr. Das at the university, and actually Jamshed was one of our research associates, and he actually did his PhD on some of the work that we were undertaking. So he has familiarity with it for a very large number of years. And when we did this
doctor's name, sorry to interrupt you, David. What's the doctor? How do you spell the doctor's name at Windsor?
DAS.
DAS.
Yes.
And Jamshed, you have a PhD under this gentleman?
Yes.
Yes, he
Dr.
does.
Srikanta Das.
Yeah, Srikanta Das.
Well, we'd like to get some papers to read. I know Robert would welcome.
Oh, heck yeah.
If you send Robert the papers, then I just wait for a summary, right? I wait for a summary because I'm a car.
I'm going to give you some anecdotal information. You can really have a lot of fun with your customers with. What you can do is you can challenge them, try to guess how thick our slab is.
Okay.
They'll say, okay, well, what do you mean? Said, okay, so I want you to do this as a matter of course, walk out to any concrete, standard concrete, and you can tell them exactly how thick it is. And I've done this with flooring inspectors. So I said, this makes you look really smart. What you do is you step off the average cracking of the slab. If it's 10 by 10, the slab is 5 inches thick. If the cracks are 12 by 12, it's 6 inches thick. It's a squaring off that slabs do, that concrete does. It's called the 1x2 rule. That's what governs your control joints. So that's how you know how thick it is. So you said, if you want to see the real difference between our slab and theirs, you can't tell how thick ours is because we don't need these.
So that's 30 times slab thickness. Is that what that is?
No, it's 1 to 2. For every inch thickness, you want a 2x2 cut. So that's why your sidewalks are 6 feet or 3 inches thick. So you see the cuts are 6 feet.
Very good.
Yeah, so it's pretty. The only difference is when you're in the desert, it's a little bit narrower than that. Then it's 1 by 1.5. I don't tell them to go by 1 by 2. Go by 1 by 1.5.
Is that because of the hydration issue?
It was the dryness because the concrete shrinks a lot more.
Yeah.
And now with E5, that's changed, correct?
Yes, that's changed. And the other thing I wanted to add, what was really interesting, got my curiosity up, is one of the first studies I saw on colloidal silica was way back in 1974 by the Army Corps of Engineers. And they did a study. They didn't look at it as a secondary cement. They did it as an additive. What they noticed when they would keep adding the colloidal silica as an additive it caused a better spread of the concrete and a more even spread, and it got around the rebars, and it helped diminish, in fact, in most cases, eliminated rock pockets and other void effects that are caused by drag. Now, that's the other thing that your competitors will do if you look at a polymer-based fiber, is you get a lot of drag. So basically, you get a lot of voids. When we used to treat concrete with, say, like a polypropylene fiber, we knew that it was going to take at least 20% more concrete sealer to be applied because it made the concrete that much more permeable. This, coupled with your material, which is in a sense, another type of aggregate. It's just a different form. It's another aggregate. It will treat it as another aggregate. So everything will be homogeneous and integrated.
Correct.
The polymers are not integrated. It is a dissimilar material. It will never work in the same way. I don't care what they tell you, what they try to show you. It does not work in the same way. Functionally, it does not work. What I see in yours is it's a functional working.
Yes. And to add to that, Bob, we have actually done testing, ASTM standard testing. What it has determined is that by the introduction of our fibers, it will increase surface hardness naturally by about 25 to 30%. So you don't need to add any chemical admixes or pozzolans to try and get you that additional surface hardness. But I think with that E5 introduction as well, I think it would make it even better, quite honestly.
Yeah, because now the even spread and plus the internal curing that you get, because when you look at a particle size, if you look at the surface, when the surface starts evaporating water, that cools the concrete down.
Right.
So the more surface area you have, the more evaporative cooling you have, the curing will be uniform all the way through. Your concrete will be exactly as hard and the same compressive value a quarter inch into the concrete as it is all the way through. That does not happen with standard concrete. The top 1 inch is always weaker, always.
Absolutely.
Even in a lab.
Yeah, absolutely. And that's because, like you said, of the hydration, right? So
correct.
During the process. So naturally dilutes the top level, unfortunately.
Yes. And see, without the cooling effect, like you saw with the 90 and 100 degrees, you know that the calcium hydroxide, as it's developing, which is a byproduct of cement hydration, becomes insoluble at 100 degrees. So what it's doing is actually stymieing development of cement. But by adding the internal curing compound, you're actually reducing that heat generation that you would normally get. So that's why you're not going to get that basically lens effect that you would normally get in a hot day.
David, for Jamshed and you to remember, this is somewhat consistent with what we're finding. 4 ounces of colloidal, which is liquid, nanosilica per 100 pounds of cement is a very good. And, you know, that would be within 20% probably, you know. But the nice thing about this product, this E5, is that it's typically saving 15% of the powder. So when you look at 15% of the powder, if I put 1 gallon in an 8-meter truck, and I did it the other day, you put it at the back of the truck and you rotate that truck, you know, for 5 minutes, you know, 7,500 turns. And this is right from Joe Shetterly. He did a lot of these things, and he was a finisher. And so he was always saying, well, there's a missing element. He and his dad, 3rd-generation finisher. And sure enough, you know, he came up with it with Purdue's help. So Purdue's a very top university, as you probably know, Jamshed. It's a well-known American university for concrete. And Luna Liu is the doctor there, the work of Luna Liu. And I think probably Robert can supply Jamshed with a few papers on a reciprocal basis to make sure our libraries are tight. So that 4 ounces per 100 for 8 meters, that gallon only costs, even with a markup, $100. So you're taking 500 kilograms of shotcrete mix, let's say. It's less money. The cement savings is less money than the admixture that caused it. Comes to the whole thing too. That we're getting in a DIN 2148, I think it is, Robert, the testing.
1048.
1048. I got to get that right. 1048. Anyway, on that, we're seeing 80% reduced permeability. 80% reduced permeability. So you basically have salt resistance, David. What we want to see is the end of rehab cycles, and this will do it. That's why Robert and I are so excited, and we've done a number of podcasts together. And this is a good one, I think, Robert, to because to recommend the basaltic fiber would be common sense. Like, why recommend a helix fiber, a steel helix fiber? Would you agree? We got twice the stiffness.
I want to get metal and plastics out of concrete. It needs to be concrete. Basically, basalt is an aggregate. It's just another form. So if you can get concrete that holds itself together, that's exactly what you want, because you're not dealing with dissimilar materials any longer. That to me is really a good end game, because you're dealing with something that is compatible 100% all the way through. You're not dealing with dissimilar materials. I'll give you a good example. I was in Oregon and they were trying to repair this bridge and the repairs weren't working. And I looked at the chloride analysis. I said, "Look, that's because you're using a clean patch." He said, what do you mean?" I said, "You need to put chloride in your patch." He said, "Well, we can't do that. We're going to cause corrosion." I said, "No, what's causing corrosion is you putting a clean patch in because you're setting up a galvanic cell. What you want to do is get them as close together as possible. You're putting in dissimilar materials." So they experimented. They had patches that they put in that were clean, patches with about 50% of the chloride contamination, and one with 100%. The ones with 100% that matched the concrete stopped having problems. I said, "Look, you're just trying to buy time. This is the way you buy time." And that revolutionized the way that they repaired their bridges. They didn't know they would have to contaminate their repair material to keep it from corroding faster.
You know, it's funny you mentioned that, Bob, because we actually provided a large consulting firm here in the province a repair method to repair bridges, the abutment walls, and the bearing plate seats, because those tend to be the areas that are mostly adversely affected due to the road salts, because they all seem to come off the structures and kind of find their way down along the abutment walls and right on these bearing seats. So we actually had a method to repair it, and they all shook their heads and said, it's not possible, you can't do this. Well, we did demonstrate it on a high load bridge where we repaired it. And they said, "Well, but we would use carbon fiber." And I said, "At 5 times the cost, sure." I said, "But it's not UV resistant, and it's going to work against it, and it's going to wick moisture, and you're going to have the same problem." And trying to help our fellow engineers understand the differences. The difficulty is, as you just mentioned it a moment ago, and it's perfect, Bob, how many people know about dissimilar metals? I do, because of my background. But a lot of people don't understand. So when our fellow civil engineers look at something, they've relied on the materials people, but there's a huge disconnect. There's a disconnect between application, and there's a disconnect between science or the engineering behind it, right? The implementation there's a gap there. And so they don't always understand that sometimes, like you said, right, you have to use the bad thing to make it work good.
Yeah, okay. Even worse, in my opinion, is truncated science, where they're using a fixed amount of influences and they ignore influences outside of that. Because when you're dealing in the field, you're dealing with kinetics. You're not dealing with just thermodynamics. You're dealing with kinetics. There's all these odd influences that you can't possibly predict or duplicate in the lab. You have to figure it out in the field first, then bring it into the lab and figure out what you did. Too many people are doing it the other way around. They make the stuff in the lab. "Oh, look how good this is. Oh, that wasn't supposed to happen. Oh, that wasn't supposed to happen." No, find it first. Find the solution, then figure out why the solution works. We've gone backwards for whatever reason.
I truly believe, I think part of it is we've become, it seems, more hands-off.
Yes.
And I think there's less practical engineers out there. I know we've had some folks who've left our organization because they didn't like the fact that they would sit behind a computer all day. And I said, "You're not going to sit behind a computer all day in this business." I said, "In our business, you're going to be in the field. In our business, you're going to get your hands dirty, because that's the only way we can understand and see what's going on." And not only that, but as we know, and Martin will tell you this with his many, many, many years of experience, walking 1 meter or 3 feet away from some structure is completely different to what you saw back there a meter ago. And
Yes.
How do you address that? Well, again, right? It's well, the book says, look, time, money, you got 3 shovels, you got 5 operators. They're all standing here waiting for you. What are you going to do? Right?
What are you going to do?
Yeah. So, you know, it's all about being able to address the situation. And yes, sometimes we make the best decisions we can, and sometimes the best ones don't turn out to be perfect, but they certainly are as educated as it can be, because we have an understanding. And half the time, the folks that are on those tools, they already have the answer for us if we only were willing to listen. You know, and it's funny because the folks who've handled our products, the trades folks, they absolutely think it's the bomb. Right? I mean, you pick up a 100-meter coil of rebar in one arm, and you can carry it, right? 10-millimeter rebar. Seriously.
Wow. It's a great product.
It weighs 38 pounds.
Oh my God.
Yeah.
It doesn't. What do you do? What do you do to keep it from floating?
Specific gravity is basically the same as concrete, so it doesn't float.
Yeah, it makes sense.
Wherever you put it, that's where it'll sit.
Okay.
Yeah.
Because we can even get aggregate float, which is one of the problems they have when they use curing compounds, which is the other reason why I want to get away from those. When you get aggregate float, because the lighter amorphous aggregates towards the top,
right.
And then when they cure it, they get a concentration of alkalinity, and it causes the surface of the concrete to start breaking down before it's even cured.
You know, it's curious because when we've run into situations where we've had folks on site and we have the coils, or we can do them in sticks as well, depending on what people prefer. But the difference between us is we only need a 6-inch overlap versus steel, which is 12. Okay. And because of our tensile strength and pull strength. And the interesting thing is that we have actually worked with some of these folks where they've said, because it doesn't have a memory like steel, we don't have to have a straightener on site. We had a customer that did a slab that was, I believe it was about 250 by 500. So it was a very large slab. He had planned to have 2 weeks to have his guys there cutting and tying. He was done in 6 hours with our stuff.
Well, so you said it doesn't have memory, so this doesn't have creep?
It had very minor amount of creep. Very minor amount of creep.
That's awesome. That is awesome. That is such a big deal for a really huge slab. Huge deal.
The fellows who've been putting in pools and gals, I guess, they've been coming to us because now they don't have to have grounding permits. So it saves
gotcha.
a lot of money.
Wow.
Because now they don't have to run that, and you know what the cost of copper wire is like now.
Oh, so,
and you know, it's not 24 gauge they're running, right? I mean, it's the heavy duty stuff, and it's expensive. So they've been quite pleased with that, and they've seen it as a benefit, even that in the mesh. We think that, and in Martin's case, when we originally talked, Martin and I, we looked at a number of different applications, and of course his culvert repair. There's a lot of flexibility there because we can literally bend a 4-millimeter, not just the rope, but a 4-millimeter piece of rebar. I can literally bend it in a circle. So we are looking at actually making hoops, but Martin found that it was a better opportunity to use and to look at the rope, because we had done all the modeling and the design with him to try and see what would best work. And Martin and his team ended up, you know, going toward the rope, which makes sense too, because you can also tension it.
This for suspended slabs is amazing, because one of the things that is not appreciated and not dealt with, this will be probably a little bit of some more new information for you. When you get on suspended slabs and you get the stack effect, you get a temperature differentiation as well as humidity differentiation. The bad part of steel that's very underappreciated is that the conductivity of steel is about 100 times that of concrete. So when you get cool, it gets cold very rapidly. And if it's touching something, then what happens, you get a dynamic where you get the moisture movement. This would not encourage that.
That's correct. Now I have to tell you that basalt rebar is great for certain applications. It isn't the same as in terms of steel because it doesn't have the same flexural strength. However, it may not have the same flexural strength, but you can compensate for it by using more. So it doesn't mean that it won't work. It just means it might be a little more costly. But as Martin had said, right now, our 10-millimeter rebar, we're selling it roughly for 55 cents a foot.
Can this be used structurally?
Pardon?
Can this be used in structural elements?
In certain structural elements, yes. We're actually working on doing columns, but we're looking to make stirrups and saddles as well. But right now, most stirrups and saddles, they will not allow an FRP for very good reasons, because you can't get the continuous structure, right? So, but I mean, what they don't see in steel is when they do that, they're weakening the steel anyway to make them. So, you know, it's just, it happens to be stronger than what we can be at the joint. But we can bend it. We're actually in the process of working with a builder, a large scale builder, to do some tests, because he wants to build multi-story buildings. And we know we can do columns, but we just don't know that we can reinforce the column, if you follow what I mean.
Yeah, and see, something like this, you heard about the Surfside condo collapse, right? In Southern Florida, where, there's a lot of reasons why that happened. One of the reasons was one of the first questions I asked was that placed in the 1980s? They said, yeah, 1981. I said, yeah, we had that garbage cement that they imported. Now, if you can put your, especially say ocean facing structures with this, you don't have to worry about that anymore, because there is no corrosion of the steel.
Correct.
So your seacoast structures and things of that nature, they keep redoing these things over and over again. Well, if you use this, you don't have to do that. And you can put in better concrete. It's rather than worry about this 40 years down the line, like they are with these condos now, they're panicking. 200, 300, 400 years from now, who cares? It will still be there.
See, and you know, to your point earlier about people not understanding concrete, I think a lot of them still don't understand that concrete likes to be contained, right? I don't think they realize that. So, and the purpose of the rebar is to really, as we talked about earlier, Martin, right, is to prevent cracking, so to hold that concrete together. But when you do have a failure, then you want to contain it. And if you can wrap it in such a way that you can then hold that structure together, you may still have some degradation of the steel inside continuing, but that structure isn't no longer dependent on the steel. It's now dependent upon the containment and the concrete doing its job. We actually, with the local county here, they were going to have to take one of their high load bridges out of service, and we only have 2 high load roads here, and those are the roads that are basically in excess of 100,000 pound load, and it's a bridge. And we, along with the county and Dr. Das at the university, we rebuilt this bridge. And Jamshi can actually show you some. If we can share the screen, we can show you some of the things we've done. But what's really interesting is we repaired the high load bridge, and that was back in 2017. And we go back and we look at every single one of our projects that we do. And every 6 months we do a report just to make sure we understand what's happening with the material and how it's behaving. And it is absolutely perfect. We also did.
I need all that data.
We're going to get that for you. We will get that for you.
Okay, good.
I have a stupid question. Maybe it's not a stupid question, but I think it's, with E5, which is largely not going to crack at all. Why can't we do this? And I really believe Roman concrete probably didn't have rebar. It was just done with the volcanic ash. I got to believe that, Robert, that with fibers of sufficient density and length, perhaps that's, what would you typically recommend, David, like a 1 inch?
It depends on what we're trying to achieve, right? So are we trying to achieve crack control, or are we trying to increase strength? Because we don't.
Keep in mind, we don't really have any problem with crack control anymore. Like you put the two together.
Yeah, we can put that one to bed. Yeah.
It's going to resonate. So why can't we do the bloody columns on a parking garage with fibers? I don't believe that you have to do it with bar. I'm not even sure that labor's worth it.
I would say we actually have different windowed mesh sizes, and we have a soft, so we have a non-resin and a resin coated. But we put the resin coating on because of the alkalinity. If we're using something with low alkalinity or no alkalinity, then we will use the non-resin coated. But if that's the case, it will literally, it's right here in my hand here. Can you see that here?
Yeah.
And if you look, I can form it and roll it around any structure. So if I want to go around a square corner, which they typically aren't, they have a beveled edge or something, or if they're a round pier column, we can do that with the smaller windowed mesh. And then we basically parge over it. We actually repaired a number of hydro poles here in our municipality as a demonstrator project for them 5 years ago. And the only thing we've had is a little bit of shrinkage cracking, which we expected because we were using a latex modified mortar. They didn't seal it when we needed to because the weather came in. So it sat for a year, but generally it has performed extremely well. And that's exactly it, Martin. I agree. You could probably use the fibers, but I would prefer to use a mesh only because then we can distribute it homogeneously around the structure.
Why wouldn't we get a density of fibers? It's going to be cheaper for placement, but the fibers, in my opinion, what would be your, you criticized me before for tests we ran where I didn't have enough fibers, but I was dealing with a pretty confident set of admixes. That was our Feng Mix 1, Robert, where we were putting mag oxide, E5, and what was the other thing we had? We had your basaltic fibers. Then I just sort of had a realization with E5 that that's all I need for my product. I don't need mag oxide.
Yeah. I need to jump in here because I have a project they want to potentially retain me on, and they're probably going to need some rehabilitation of the concrete. And when you're telling me about the wrap like that, have you ever tried this with a passive cathodic protection?
Well, I mean, yeah, it would act naturally as that because the rebar was exposed. So,
yeah. Well, suppose we add like a zinc to it or to your parge coat, would basically fool the anode.
I guess to de-ionize or to take away the galvanic charge, right?
Correct.
Yeah.
Correct.
So I don't see it having any adverse effect at all. In fact, if anything, it's neutral, right? So you could do whatever you wanted in terms of your zinc coating.
That'll take a bit of work, but that's some promise because with a lot of these seacoast structures, if we can move anode away from the steel, we can at least preserve it. And then keeping it wrapped like that, like you said, contained, we can really reduce the amount of repairs that they have to keep doing because it's an accelerated pace. Because a lot of these structures, they're doing repairs in 12 to 15 years on these structures that are supposed to last 50 to 75 or 100 years. So if we can extend that lifetime, again, you're looking at reducing the carbon footprint every time you do that. So basically, you're ticking all the boxes that they're looking for. So not only is it on the front end, but on down the line, we're affecting the carbon footprint as they go, and that's something I don't think they've anticipated. No, and that's something I would like to explore.
For sure, we'd be more than happy to work with you directly on that and to provide some of the rehabilitative engineering if you need it as well. So, interestingly enough, to that point, there was a state on the West Coast, which we won't tell you who they are, but we made a proposal to their Department of Transportation and to introduce our material, and they were very interested. And it took about 6 months to go through their whole vetting process. And they finally came back to us and said, now, of course, they're very environmentally conscious, right? They came back and said, you know what? I think we're going to stick with carbon fiber. And I said, what? They said, yeah, we're going to stick with carbon fiber. And I said, but it conducts electricity. Why would you use that? You're creating a naturally occurring degradation agent to your fix. Why are you doing that to yourself? And it's not even environmentally friendly, and it's in earth-touching applications where there's the potential for some contamination. I'm sure minute, but still not the point, right? And I just couldn't get over it. And it's that whole, I think, mindset that people really have a hard time looking at something different. But it's so simple, it should be easy, right? But it's not.
No, it's not. And let me tell you, I say this and I repeat this for a lot of the presentations I make. I said, for all the blather we hear about, oh, wait, we need to change, we need to do this. At the end of the day, the only one that likes change is a wet baby. They don't want to change.
It's true. It's true.
I mean, you got to drag them kicking and screaming into change. So the best thing to do is present this in a way where we're tickling the areas that they like. Oh, carbon footprint, you're doing what? That's what you tempt them with. Forget the performance. This is what they want to see.
Yeah, but they don't want to see that either. They say they want to see that, but that's not.
Yeah, because if they get those carbon little marks next to their name, oh, they're happy. If you play to their ego, play to their priorities, that's sometimes the best way to go in. No matter how technically sound you are, like you just found out, it's falling on deaf ears.
What we're seeing, Robert, in Canada is a tremendous over-design going on by large engineers that I believe have consolidated, and they really look at it and say, well, why not make the subway wall like Yonge and Finch in Toronto a meter thick?
Yeah.
You know, when the wall from the 60s is still there and it's 16 inches thick, and they're tying into those walls. David, 1,000 kilograms of steel in manufacture is 7,000 kilograms of CO2. What would be the comparable when we look at your bar? You're basically melting it, right? So it's nowhere near the same process. Do you have a relationship in terms of 1,000 kilograms of basaltic bar?
In terms, Martin, of the manufacturing carbon footprint?
Yes.
I honestly don't have that readily available, but it really is, honestly, it is really only a factor of the energy that is required. There is no byproduct. There is no waste, no nothing. Now, remember that this material is also basically resistant to heat up to over 1400 C. So to heat this, you need a very special furnace, and you need a rhodium bushing, because it's the only exotic metal that won't basically melt at that level, but it does degrade over time. So it is costly to manufacture, but to fiberize it, it is a very, very minor amount of energy required in comparison to the smelting of steel.
Robert, let's try and nail that down in the coming weeks. I think it would be useful to have an answer for that. It's not 7 times the weight.
Well, I'll be honest, that one's outside my wheelhouse. You guys have at it.
Well, it's David, I think you know the energy involved in melting it.
Yeah. I know what it is, but I just don't know the comparison to steel. So we'll look into that, and we'll try and furnish that back to you, Martin.
I know when you smelt the rebar, it's going to be 7 times the 7 times the CO2 of the weight of the rebar. So anyway, it'd be just nice to have. I think the fibers and E5 are the future.
Yeah. Well, there is no CO2 emission from what we're doing, right? There is none.
There you go.
There is zero.
Other than burning the energy.
Other than the cost to create the energy that is being used. But like I said, we can use a low energy source and use a transformer to create a high energy source. It depends on where you want the cost to be. Do you want to be cost in energy, or do you want to be cost in conversion of energy? So transformers can be expensive. So it just depends on, on what you want. Obviously, you'd like to go somewhere or have the manufacturing done in an area where the kilowatt hour cost is relatively cheap in comparison to what we have, which is 13 to 15 cents a kilowatt hour, right? But there is zero carbon emission or zero CO2 emission when they're melting this rock, because there is none. Like I said, Mother Nature did all that work.
That's a real attribute right there.
Is there any reason why fibers at the right density wouldn't replace the rebar? We just have engineers that are used to designing the rebar, right? I mean, it doesn't seem to me that it wouldn't work with an E5 matrix.
Well, you have to keep in mind too, right? Anytime you introduce a fiber, no matter what it is, you are going to affect the compressive strength of concrete. So there is going to be some, even though ours may not be as detrimental, it will still affect the compressive strength. I believe that is a concern. If you're doing slab on grade, shouldn't matter, right? But when we're talking about suspended structures and other things, it does tend to play into the concern, right? Unless you can, of course, reinforce it accordingly. Go ahead, Jim.
Can we share?
Can we share something with you quick?
Yes.
Go ahead, Bob.
I was going to say that the E5, because of the density it gives concrete, I think that if you use the system that we're talking about right now with the E5, if you go mono on mono with standard concrete, you're going to be at or better than what they have for compressive value.
Good. Well, that'd be awesome. That's utilizing the fiber at the same time?
Yes.
Oh, okay.
Yeah, you're not. you're not going to weaken that below the standards that are currently being specified. Because right now, E5 gallops past standard concrete.
Okay.
It's much stronger.
Yeah. Can we share a screen?
Yeah, can we share something with you guys quick?
Yes,
Yeah.
please.
Is Sarah there? You there?
Can you see it?
No, not now.
Not yet.
Just,
Jam, she's going to find you something.
yeah. Yeah, just 1 second here. So we have to go. Where's our screen here? So
Your
I'm
share
gonna
screen.
Oh,
have to be
how's
removed.
disabled it?
Yeah, it's disabled right now. We can't do it.
Yeah. Sarah's, I think, left the building. So,
Okay.
but we can insert it
Splice
later.
Yeah, splice in later. Yeah.
Oh, what I wanted to say, I think you cannot replace fibers with rebars. And the reason is the length of the fibers. You know, they are very good in preventing the shrinkage crack or micro cracking.
Yeah.
But when it comes to load bearing functions, they're not as good as rebars, you know?
True, but I'll bet you it'll work.
In
Yeah,
certain applications, sure.
Yeah.
Yeah, but if there's a secondary support, but you're not going to get any engineer to approve something like that without a contiguous reinforcement all the way through the concrete. It's just not going to happen, not in our lifetime.
Yeah,
But yet the arches for Roman concrete exist, right?
Yeah, it doesn't matter.
It,
You show them Roman concrete's been around for 2,000 years. Okay, but what about a reinforced concrete? Suppose the deflection and
I know that I know we're fighting City Hall with that,
yeah,
and we're going to take one step at a time. But
yes,
certainly I would be interested to put it against Helix, and to see how far we can go with it in certain applications. Keep in mind in ICF, they're getting rid of the rebar, putting fibers with E5 now, Robert, in ICF walls.
See, and you know what? And that just contradicts everything, doesn't it, with ICF walls? Because, I mean, it's an unnaturally occurring environmental disaster, right? I mean,
yeah.
Right? And yet, we talk about going green and we're using ICF. Well, what does the matter with us, right? Where we could do this properly, right? We could do this properly with the right reinforcement, probably and more likely with the E5 mix and using our reinforcement material. But you know what? They're looking for ways to speed up the production, right? So that's all it's for. There's no other real benefit. I mean, yeah, I get it. It provides some insulative properties too, but it's not a nice thing to have, right? Everybody's been pushing away from the use of foam, and here we are using it.
Yeah, I don't.
Material.
I'm good with the fact that walls don't crack anymore, and you can get a basement wall done with formwork.
Yeah.
True.
It's I wouldn't specify. I did a lot of ICF over the years, but it was just some people fall in love with something and they'll use it.
It's going to love this. Is up in Canada, there's a gentleman I regard him as being one or two best experts in the country on curling of concrete. His name is Keith Robinson. When he sees this combination, he's going to go crazy because he'll be able to specify concrete where he doesn't have to put in all these control joints. The concrete's not going to curl. The concrete's not going to crack. Because right now he's doing a really good job of basically linking between divisions 3 and 9 in the construction documents. And the other guy that we need to bring into the fold here is a gentleman by the name of Chris Maskell. And he's basically the head of NFCA, which is the Northern Floor Covering Association for Canada. And he's probably regarded as one of the top 5 peoples in North America of an expert. When he sees this, he can't endorse it, but what he can do is he can make introductions. And I think we can get this into the flooring industry very quickly, especially with these suspended floors, because they've gone to gypsum and lightweight concrete and all these other things. We can give them concrete of equivalent value and strength, and they can probably go a lot thinner.
The other thing is workability, because typically when you look at the typical steel fiber, for example, which seems to be the go-to, you got to scarify a floor.
Yeah.
Right. This you don't have to, and if we can address
exactly
address the issue,
put it in, and they can install a floor in a month. They don't have to wait 3 months.
Yep. Yeah, and the beauty is, of course, no micro cracking. additional surface hardness. We can, if they need a pozzolan, I guess. I don't know how does the E5 react with like a hardener or.
You know, don't need it. They've got an integrated system. They've got a finishing aid they put on that completes the reaction. They don't need to put a curing compound on or a hardener. No. Basically, it's as hard as you can get without polishing.
Oh, geez.
And that's the other thing I've been battling with some of these specifiers on. I said the density of the concrete has very little to do with bonding. It is the polishing, because if you look at the, say like a microsilica and calcium silicate under a microscope, it's very craggy. There's a lot of places for the resin to grab and bite. So even though it looks real dense, it doesn't look like it's going to stick. The only problem you have with that, that's one issue we have to deal with, is dew point. Dew point, because what happens with a really dense surface, it takes only a slight amount of water to create a bonding issue. So it's the only problem we have is making sure they monitor the site correctly. Because if they monitor the site correctly, they will have no flooring failures, period. Zero.
You know, it's interesting you mentioned that, Bob, because we the same builder that we're working with on this development of columns for multi-stories, they also were pouring a very large concrete section at their facility, and I think it was somewhere in the area of about almost a 200-meter pour. So it's pretty big. I think it was a 6-inch slab. Were you there for Jim? Were you there for that? Yeah, 6 inch.
The parking lot?
Yeah.
And it was 2,400 square feet.
Yeah, it was. Yeah, so it was a 6-inch slab again. This was an exterior one. And instead of putting any reinforcement, welded wire mesh, whatever it was, we determined where they were going to cut their control joints.
Yeah.
And we put rebar in those control joints every 2 feet. And now it's been on the ground for 2 years. They have no curling. And it is absolutely doing just fine. Like in terms of what you would expect, because you expect to see that curl in all likelihood, right? With no reinforcement or anything in it.
Yeah, and also with the newer cement, it's almost unavoidable. You will get curl once the temperature goes above 60 degrees Fahrenheit.
Yeah, and they poured, I think it was end of October or something. So it was kind of an ideal time.
Yes, it was.
It wasn't too hot.
Yeah, that's ideal.
Cold for them, so it worked pretty good. But in terms of using again the rebar, to act as basically if you will, a control joint, or in this case, a load transfer dowel.
Yeah, I'll give you an example. When I was still in San Diego, Avery Dennison had me go down and go look at 3 of their warehouses because they were freaking out because the concrete curled so badly. They'd caulked the joints and it was extruding the caulk almost an inch in some places. So what do? I said, okay, well, you're going to take the caulk out. And what I want you to do is prime the entire surface with an epoxy primer and leave it alone for about a month. I said, why? I said, because you're going to relax the concrete. The curling is going to settle down. We should get rid of most of the curl. And that's exactly what happened. So I showed them an opposite way of doing it because they would caulk first and put the coating down. Said you have to do the opposite. You got to prime it, then go ahead and clean the joints. Once it settles down, put in your caulk, then finish your floor. And that's the way they fixed it.
Wow.
So they were going to do all this other expensive crap. So you don't have to do that. Just change the order.
You talked about bringing Chris Maskell on a show a few weeks ago. We should do one with David. And,
yeah.
And really explore combined experience there.
Yeah.
I have to tell you, Martin and Bob and Jamsheed will tell you, the amount of well-educated, knowledgeable people that are living in the dark ages is staggering.
Really is.
Especially in this industry, right? And I get it, their grandmother, their grandfather, aunt, uncle, they always did it this way, and this is how they're going to do it going forward. And Jamsheed saw it firsthand the other day with a contractor, said the exact same thing. Well, you know what? I don't know. I've always done it this way. We've always done it that way. Nobody wants liability, but even when you present everything to them and say, look, I'll take the liability. I am that confident that I know this is going to be your outcome. You still can't convince them. And I give them the material.
Yeah. That's the wet baby thing.
Yeah, yeah, exactly. But it seems to be more and more, it just seems to be more and more prevalent. I do know that one particular case, when we spoke to our transportation folks, they had said, well, we've kind of overly invested in carbon fiber and GFRP in terms of, what we want to do. And I'm like, okay, but why wouldn't you consider this? And they said, well, we just don't want to. And then they would put up roadblocks saying things like, well, there needs to be 3 suppliers. And I'm like, look, just try it. I mean, and if you need 3 suppliers, fine, I'll open up 3 companies. I don't care, right?
One of the things we can do, I'm pretty good at this, is what you do is you set up, rather than saying, okay, this or equal, what you do is you find things that can accomplish what you can do, as long as you can find 2 other sources that can accomplish pretty much what you do under a performance standard. You basically write your own ticket without being proprietary. You do a performance standard, a performance specification. This is what the end product is going to do, and here are the steps that how you validate this works. Then what you do is you find other products that work like that. For example, with E5, the only other product I've seen that works like that costs 10 times as much. And there's 2 or 3 of them out there. Well, fine, they're equivalent, bring them in. They can't compete, it doesn't matter. That's the way around it, because the government will never take a proprietary source unless you're Monsanto. If you go in and you give them a performance spec, and there are materials out there or systems out there that can meet the spec, that's what you give them. And here's the other 2. If yours costs 10 cents a foot and theirs costs $20 a foot, it doesn't matter. It's the performance, it's not expense. If you can find equivalent systems out there, I will help you build the spec.
If you get the commercial market, right, Robert?
Yeah.
Take it there.
Yeah.
And be a little bit like, I don't see any reason why David's bar wouldn't be very successful with E5.
Correct.
Fiber with E5 on big slab and bar. And with commercial guys that want the money, right?
Yeah.
I mean, in the special foundation area, the good thing about that, David, is it was always design build, right? Because, the more innovative guy with the soil and with the solution, that's where I got a lot of advantages. But a lot of that's design build. And so that's essentially what you're doing, David, right? You're doing design build. Right?
Literally. Yeah. And the interesting thing is, Martin, is that most everything that we do, we will do the engineering work. And we also stand behind the information and the product, so that if people have questions, we'll show them how to use it. We'll show them how to properly apply it. And most importantly, we will help them design it if that's what they require from us. So you're getting not just the material, but you're getting the engineering behind it, because we know that, unfortunately, we've seen it firsthand that we have to handle some materials a little differently. So not all admixes get added the same, right? Not all materials get laid the same. There's ways to do it. So, and to be effective and to have the right outcome. But it's, again, it's education and it's application. And the more they see it, especially the folks when they don't have to have, orange hands, and you can literally cut our 10 millimeter rebar with bolt cutters, and our mesh you cut with a pair of scissors or an X-Acto knife, and you can cut it to the shape. So, and the same with the fibers, right? The fibers are very easy to use. Just like every fiber, it will be itchy, but it's non-toxic, unlike the polys, and it won't wick moisture, as Bob said earlier. So there's a lot of real inherent benefits, and we try and share those with folks so that they understand how that works for them and their folks. But it's
also the R value.
And the R value, yeah. There's actually an R value with our material.
Well, are you comfortable doing detailed engineering in the States, David? Then?
We can do detailed. We don't have. You have to be mindful of states where you're at, depending on whether you need designations or not. We don't have designations in all the states. We have them in a couple. It's not hard to find a fellow PE or a local one to help them understand what we're doing. And then if you do the work for them and they know that it's legitimate, they still have to review it as if it's their own. We understand that because we would do the same as you would, Martin, as you know. Once they build confidence that we're able to support them, whether we would need to engage them to do the work for us, we could teach them how. And we have all the information and all the data to be able to apply. So believe it or not, FRPs are in the ACI code. It's just trying to get everybody to understand application of them, but they're so used to what they were doing that it's very difficult to get them to make that paradigm shift.
Very good. So I do value engineering today. I don't insure myself anymore for detailed engineering. I crossed over to the value engineering world, and I believe Robert would be more in that support for the value engineering, the solution, and the inventive nature of saving money with sustainability. I think it's been great to have you today, and think about that flooring one with Chris. You know, I think he would enjoy meeting David, even if you do it on your own phone call, Robert.
Yes.
Because I think flooring is a key application for
it's a huge
P5 with the basaltic fiber.
Yes.
To go back to that control joint scenario, was that needed, David, in your opinion, that you needed to put those dowels?
For that big, for that one slab I just mentioned?
Yeah. How big was the slab again?
Yep.
2,400 square feet.
Oh, no, it was more than that.
More than
Yeah, it was about, I think it was about 20,000 square feet.
2,400.
Yeah, it was long and wide, right? Where the dowels needed, the fellow who designed the driveway, he's a fellow PN, so that's what he spec'd out and he designed, and he wanted to use that. So we looked at it and we said, there's no reason you can't. I just don't know I don't know what to expect because we'd never done that in that application. But he didn't have he had no curling, and he also wanted to protect, I think, as well for any degradation potentially with the sub base, right?
Was that 2,400 square feet or 20,000?
20,000.
20,000.
Yeah.
It'd be interesting to try with E5.
Yeah, I'm gonna jump in here because I don't think the dowels did anything.
Me neither. Yeah.
That's what I'm saying.
In fact, the reason why I don't think so is because he went out there and he was looking for cracks. If you put a dowel in something like that and the concrete's going to restrain here, what it'll do is it'll have smaller restraints out here at the end of the dowels. You should have seen parallel lines. If there was no parallel lines, the dowels did absolutely diddly squat.
Yeah, and you know, that was a different application, Bob. That's a different one. This is an actual driveway. The other one was a covered slab.
Okay.
He wanted to do that, so we didn't understand why he wanted it at first.
Made him feel better.
Yeah, well, I think he was more concerned about. I think he was more concerned about the slabs shifting. So he was trying to hold the slabs together.
Yeah,
that's what I think is. I think that was his end goal, quite honestly.
Gotcha. Okay.
Yeah.
Now, if you pour two individual slabs, yeah, absolutely put a dowel on there.
Yeah, that's what.
Because you don't want it doing this. You don't want, you don't want to shimmy. You don't want any of that stuff.
That's what I think his end goal was.
Yeah, you put it in a slip dowel. Yeah.
Very good. I suggest it's pretty good for today. I was going to knock it off, but Jamshed, help us out with the edit if you could.
Yeah, sure.
And particularly inserting some of David's material. And if it would also be very useful if we could combine a little bit on some marketing together. I'd like to help David.
Well, we appreciate that.
I'm sure Robert would as well. This to me has a lot of potential, Robert. And I'm glad you had the ability to explain E5 and that we have the ability to put two great products together.
What I'll do is I'll forward an article I did way back when, I think it was 1986, because we were doing restoration of the Frank Lloyd Wright Falling Water and some of these other ones about corrosion of steel and everything else. I have really been an advocate of moving away from steel, but I don't like epoxy coated steel for a variety of reasons. One, it doesn't bond to the epoxy. And two, it exactly the opposite of what they claim the epoxy will hold up to is true. I actually used to butt heads with this guy by the name of Ken Clear. He was a former Federal Highway Administration official, engineer, and he went out on his own, and he was a big proponent of epoxy coated steel. and he and I butted heads. Well, he went out and looked at over the Florida Keys, and a bunch of the concrete sloughed off the side. Was how you saw this pretty light green epoxy coated steel, but the concrete sloughed off. There's some other areas where the corrosion was severe. Well, the corrosion was severe because they were saying what it can have up to so many nicks. I said, the smaller anodic area, the more likely you are to have what's called knifing, where the corrosion just cuts right through the steel because it's not spreading out. You know, what you're telling me doesn't make any sense from a corrosion standpoint. Well, Ken had a crisis of conscience, and he actually said, okay, I don't recommend it anymore. And the Concrete Reinforcing Steel Institute actually sued him. Well, the judge determined that the lawsuit was not only frivolous, they were trying to intimidate and put him out of business. And he had to spend so much money in the lawsuit, it ended up putting him out of business. He just didn't want to do it anymore. So I've been semi in touch with him since then. You know, I feel bad for the guy because that's how things are. What they're showing is something that gives us an option that's better than epoxy coated steel because we don't have to worry about anything chipping. We don't have to worry about anything not stick. The concrete's going to stick to that because it's an aggregate. It'll treat their fibers and their mesh just like it would any other aggregate. It's a married system. You're not dealing with dissimilar materials. Everything there works and makes sense. So that's why I was asking you those questions about that, because I'd love to, that's the direction I would really like to see us go in, especially for floors. This is an integrated floor that will never have a problem. Put E5 in the fibers, we're done.
Joe Shetterly's bridge decks, he's done 200 bridge decks, which is his claim to fame lately. He's putting epoxy bar down there. And
yeah.
I think Dan McCoy is the engineer that sometimes shows up. But if you go to their website, it's pretty good and you can get these. But in his bridge deck, he's got epoxy bar. And
yeah, on the top part, you don't need the bar. You could go in with this instead and get away from the bar completely.
And the engineer would want something, but I think it'd be a pretty quick PO for these guys.
Yeah, because all the structural components are underneath it. They don't need the steel in there. That's just to control the cracking. That's all it's doing. So they put epoxy because they're worried about de-icing salts.
Yep.
What they have is they don't have an issue with de-icing salts, not with basalt.
And they don't have an issue with de-icing salts with E5.
Correct. It is a non-issue now. They don't have to worry in the future that the epoxy isn't going to degrade at some later date.
David, I'll send you that one video with Dan McCoy talking, and he shows it. You can see the green rebar in the background. Right?
Yeah, we would like to, if possible, cast some beams because we have our own lab. So we would like to cast some beams. We also have the university lab as well.
What if I brought, listen, David, it's a chance to get face-to-face, buy me lunch and I'll bring you some E5.
Oh, absolutely, Martin.
So let's follow up. Like I can, I just carry it around in gas cans, but clean ones. And, you would be a long time using up 5 gallons, right? Because 5 gallons is 50.
No, I go a long way, especially as you said, with 4 ounces per 100 pounds of concrete. So,
yeah,
I believe we can use E5 with dry mix shotcrete and with your fibers.
Oh yeah.
That would be, because we could just meter in the water or the E5 with relatively.
So the compressive strength of E5 compared to normal like 30 MPa concrete.
Typically, you're going to get better. So, and that's why we dropped the cement 15%. Like a guy who's pouring a 350 kg mix, he's generally pouring it for different reasons because he wants to pump it or he wants to have the paste. But when you put E5 in, you create this fine paste that you can drop the cement content 15%. So similar to what Robert would say, you get a higher strength, and that's manifested by, we can take some cement up. Right.
But assuming
but let's get you guys testing for sure. If you've got access to a good university, we'll support that.
But I'm saying, assuming that we keep the cementous ratios the same, and we just put the E5 in, can we expect it, instead of being a regular 28-32 MPa, would it be incrementally like 10%?
I would say at least 10, maybe 5 to 7%, like 5 to 7 MPa more.
So we
Thank you,
jump
Robert.
around high 30s,
Yeah,
right?
and where you're really going to see it is downstream, because the initial development of calcium hydroxide takes about 28 days. So the conversion is occurring within the first 28 days, but you're going to see the strength gain go very rapidly upwards as opposed to standard concrete. At 6 months, it's going to, the E5 concrete will, even with your fibers, will greatly exceed that even really high quality, low slump concrete that you would normally expect to be weakened. You're going to see better numbers than you'll see with those.
Oh, so you'll see improvements post 28 days then?
Yeah,
So
well past 20 days. Yeah.
Okay.
Yeah, well past. Yeah. And it keeps going up. I believe that if we looked at their numbers, you took your fibers, and let's say that the concrete is targeted to be 5,000 PSI at 28 days. Well, this will be, then you're hoping for 6,500 PSI by the end of the year. I think with the same mix with E5, you'd probably see about it. It'd be more like 8,000 PSI.
Do you find that adding your E5 makes the concrete any more brittle, or is there some value?
Okay. Increases the ductility.
I like that even better. We've been testing some beams that we've been reinforcing with our rebar, and it's amazing the level of ductility that we've had. At failure, we're about 18 MPa, so what is that? Maybe 17,000 PSI, maybe.
Okay.
Somewhere around there. Our highest one was around 28,000 PSI.
So normally, yeah, I know what you mean, because I was a very outspoken critic back in the 90s when they
David, I got to get going.
Okay.
Listen, but you guys, if you want to keep talking, I think it might be recording, but because Sarah's on the other end, but we can edit the back of it, Jam Shed. You're going to help me, right?
Yeah, right.
Okay. We better put it.
We could probably talk. It's probably a good time to end it, because I've got all these things.
Yeah, we can talk about all sorts of stuff, but yeah.
I know.
Awesome.
Okay.
All right.
Hey, thanks, gentlemen. Great to meet you guys.
All right, gentlemen. Thank you.
Nice to see you again, Martin. Thank you. See you, Bob.